Welcome to the Dr. Jimmy video for Section 1.2. I'm going to look at solving equations, and that all relates also to factoring. So, prerequisite material that we'll look at again. So, topic 1 here, looking at some basic things about expressions. So, for instance, I might write 5x cubed minus the square root of 3x plus 1. So, just a basic algebraic expression. Notice that an expression is just a clause without an equal. Now, in expressions, we have factors. So factors are parts of products. So something like 4x plus 3 is a factor in the expression of that times another factor, x minus 2. So this is written as a product. And then we also write expressions. Instead of a product, we might write it as a sum and difference expression, such as 4x squared minus 5x minus 6. So we see this as a sum. So we have expressions that we write as products, others we write as sums. So factors or terms. Terms are part of a sum, factors part of a product. Notice that in this, if we look at order of operations in both cases, in this example of a product, we have a product as the main operation, and then inside that we have other things. So it's possible that some of the factors in the product have terms. But the main expression is written as a product first, and then the factors have possible terms. If we look at this example with terms, we have the main process is a set of terms which are being added or subtracted. Within those terms, it's possible that a term might have its own factors, but they're not factors of the entire expression. So 5 is a factor of 5x, but not of the entire expression. So we see this as terms. Up here we have 4x is a term of one of the factors, but not of the entire expression. So keep those straight. Sometimes we have an expression written as a product, and sometimes written as a set of terms. So, as a product, we might say that it is a factored expression, and as a set of terms, we might say that it is expanded. Okay. Now, the factored expression here, 4x plus 3 times x minus 2, is actually equivalent to the expanded expression, 4x squared minus 5x plus 6. So, whether it's expanded or factored doesn't make it a different expression. It gives us a different form of the same expression. Okay, now looking at a second set of ideas, starting with expressions again, which are just powers. So that's a variable with an exponent, so a power expression, but it may have a coefficient, so such as 4x cubed. But something like minus 2.6x to the minus 2 is also a power expression. It has a coefficient minus 2.6. It has a power x to the minus 2. Five square root of x, although written as a radical, it's the 1/2 power, so we could also say it's a power expression. Okay. Now, if we say it's just a power, these are all single terms. So we might string them together to make an expression that's longer as a sum or difference. And so in those settings, we look at polynomials. So consider expanded form. So a set of terms so if it's a polynomial, the only terms that we just see are constants or whole number powers. So a few examples, 3x squared plus 2x minus 6, for instance, or 4 plus 5x cubed minus 7x, so cubed would help. So polynomials, we have constant terms, which is a minus 6, and then everything else is a power, like a 3x squared, but the exponent is a whole number. So we might have other terms in expressions that look very similar. Something like 3x to the minus 2 minus 5x squared plus 7. But it's not a polynomial because of the term, which is not a whole number power. We have a negative exponent. So a one-term polynomial is in many cases called a monomial. So examples of those would just be basic power functions like 3x squared, one term. If we go to two terms, it becomes binomial. So 4x squared minus 6, for instance. Three terms becomes a trinomial. So 2x squared minus 6x plus 7. Three terms, trinomial. Now we could continue this, four terms, quadrinomial, and so forth, but usually at that point we begin to just call them all polynomials, but it's useful to have monomial, binomial, and trinomial. Now, another term which has to do with 1 is what would be called a monic polynomial. So, but it's different than monomial. It's monic. So, the leading coefficient is the number 1. And what is the leading coefficient? Well, it has to do with leading term. If you look at all the terms in the polynomial, it's the one with the highest power. So if we have x squared minus 2x plus 1, it's monic. The highest power is the term that has the x squared, and the coefficient is a 1. Usually not written, and so we just have x squared. So that makes it monic. And then we have degree. We could say degree of a term is what we would see as the power. So 3x cubed is degree 3. Degree of a polynomial is the greatest power. So if I have 1 minus 2x cubed plus 3x minus x squared, it has degree 3. That's the highest of the constant, the cube, first degree, second degree. The terminology, the leading term, would refer to the third degree term. So 2x cubed with a leading coefficient is the minus 2. So, polynomials, expressions, different powers. Move on to equations. So, if you write an expression and introduce an equal, and then another expression, this would be called an equation. Two things supposedly equal. When you write down maybe an example of equation, 4x squared equal 5x plus 6, and you read off this, it's a complete statement. 4x squared is equal. So we have the verbs, we have the nouns, we have a complete statement. 4x squared is equal to 5x plus 6. Where an expression is just a clause. Given an expression with variables, we may substitute values for the variable. So, for the substitution x equal 2, in the expression we would have 4. 2 squared equals 5 times 2 plus 6. So 4 times 2 squared is equal to 5 times 2 plus 6. I compute this. Left side of the equal I have 16. In this case, on the right side of the equal I get 10 plus 6, also 16. So the statement with that particular substitution is true. Okay. In that case, we say that x equal to that particular substitution is a solution. So, solution of an equation is a substitution for the variable that makes the statement a true statement. It's also possible as if we put in x equal 1 as a substitution, then it's 4 times 1 squared is equal to 5 times 1 plus 6. So we still get a statement. It's okay to state the statement. We look at the result. 4 on the left is equal to 11 on the right. It's still a statement, but we notice that that particular statement is false. You can have true statements, you can have false statements. But when it's false, we say it is not a solution. So, and sometimes we talk about a solution set. So find all the substitutions that make it a true statement, which may be more than one. It might be one, it might be infinitely many. So it turns out for this example at 4x squared equal 5x plus 6, Well, we determined 2 was a solution, but also it turns out that minus 3 over 4, when substituted, makes a true statement. And those end up being the only 2. So it has a solution set of 2 things. So, expressions, polynomials, powers, equations, solutions of equations. So, now, look at the topic, factors. So, and we really want to look at expressions and factors. So let's look at numbers a little bit first. So a number like 12, we can rewrite it in terms of factors, which are 3 and 4. So 3 times 4. But as in many situations, we might have other choices of factoring. 12 could also be written 6 times 2, or 12 times 1. So a lot of possibilities. Now, we could write 12 as 3 times 2 times 2. So what I've written here, all the factors, 3, 2, and 2, are prime. So a prime number has only one way to be factored. So that would be itself and 1. So the only factors of 3 are 3 and 1. 2 are 2 and 1. So if we go to a prime factorization, then there's only one way to do it. So in terms of prime numbers, 3, 2, and 2 is the only way to factor 12. Now, many cases, we wouldn't write 1, but if you wish, we tend to not write 1s, but if you want to, in certain cases, notice that you can always put a 1 in the factorization. It's really still the same factorization. And then in our prime factorization, every factor we write in this case smaller than the original number 12, which would be true as long as the number wasn't prime itself. Now, let's move to expressions. So I'm going to write 4x squared plus 2x minus 6. One thing we can do with expressions is look for common factors. This expression has 3 terms. Each of those, 4x squared, 2x, and minus 6, have a factor of 2. So will be 2 times 2x squared, a 2 times an x, and a 2 times a minus 3. So one kind of factoring is to look for common factors. Is the factor the same in all the terms? So I start with terms, I factor out a 2. Now it's a product with a second factor, 2x squared plus x minus 3, which has its own terms. So what about other things besides just looking for common factors? So we looked at numbers, but the same as with numbers, we start with an expression, we would somehow want to move towards smaller expressions, in some sense of smaller. So in general, the smaller might be a little hard to get a hold of, but with polynomials, smaller refers to the degree being less than what you started with. If we take 4x squared minus 5x minus 6, it could also be written as a set of factors, 4x plus 3 times x minus 2. So we start with second degree and end up with first degree. So it's the kind of factorization we want to look for with polynomials. We have some larger degree factor. What we end up with has less degree. So we can consider a lot of factoring. Most of our factoring involves polynomials. So let's consider factoring polynomials. So factoring polynomials has a lot to do with solutions of equations. So we're going to take those two ideas and bring them together. One basic fact is looking at roots of polynomials. So, if we say we have a root of a polynomial may be indicated as capital P of X, that's referring to a solution of the equation 0 equal to P of X. Now, 0 equal P of X. The word root is used for the solution, but the word 0 is also used in that setting. So we might say we're going to solve the equation 0 equal polynomial, find a solution. We could also say we're going to find the root, or we're going to find a 0. They all mean the same thing. Now, big fact here. If you take a root or a 0 for a polynomial, then you actually have also a factor. So we're going to take advantage of that. Roots, or these solutions, are really just another way of looking at factoring. So, for example, x equal 2 is a root of 4x squared minus 5x minus 6. So I substitute in 2. And I find, oh, it is a 0, so I have a root. But that means x minus 2 is a factor. So factors and roots. Factors, solutions go hand in hand. Notice that the root and the way it appears in the factor are opposite sign. So root is plus 2, factor is x minus 2. Now, make a note here that in this association, the roots associate with monic factors. So we have the root 2, we have the factor x minus 2. So that leading coefficient is a 1 in this association. So what about a factor? Such as 2x plus 1. Associated root, well, what we have to do is write this as a monic polynomial, so that means take the coefficient of x, factor it out. So I have to factor 2 from x, and from 1 it leaves a half. So now I have the association of the root being 1/2, not the original expression with a 1. So this association is with a half and not 1. Oops. Excuse me, minus a half. Remember, change the sign. So if I take a polynomial, in the factored form here of x minus 3 times 2x plus 1 times x plus 1, it has the roots 3 minus a half minus 1. Okay, so I can read those off from each factor. Noting the 1, I had to factor out the 2. So we get opposite sign here with the 3, opposite sign but dividing through by the 2, minus a half, opposite sign from the plus 1 here of minus 1. So, if I write a polynomial 6 times, example above, I still get the same roots. All I've done is change the leading coefficient. Or I have a common constant factor. So many different polynomials may have exactly the same roots, but then the only change from one polynomial to the other in that case is a common constant factor. Okay, now make a big look at these factorings, and we could ask, is x minus 3 a factor of a particular polynomial? In this example, is it a factor of 2x cubed minus 3x squared minus 8x minus 3? So, well, we could think about factoring and different things you might know about that, but we could look at the associated root and do a check. So the associated root, x minus 3, if that's a factor, we would be looking, is x equal 3 a root? So substituting x equal 3, so we've got 2 times 3 cubed minus 3 times 3 squared minus 8 times 3 minus 3 is equal to, 0. Oops. So the answer to this question is yes. X equal 3 is a root, so x minus 3 is a factor. So we have this association between, and it's one way you could attempt to factor. Try different numbers. Are they roots? If they are, you get a factor. If not, that's not a factor. Now, let's look at some quadratic polynomials, which means degree 2. So if we're looking at degree 2 polynomials, so if we have a quadratic, we can factor any quadratic if we go back to the quadratic formula. So if we take a polynomial ax squared plus bx plus c, so we have coefficients a, b, and c, then the quadratic formula says the roots can be computed as minus b plus or minus a square root of b squared minus 4ac, and take the whole thing and divide by 2a. So associated with a polynomial, if we set that equal to 0, we have a nice formula for the solutions. But if we can solve and find the roots, we've also found the factors. So take the polynomial, for instance, x squared plus 2x minus 3. Look at the roots. So x equal, let's see, b would be plus 2, so we get minus b, and then we have two possibilities, plus or minus what we get in the square root of b squared, so 2 squared, minus 4. A is the coefficient of x squared, in this case a 1, and c is this constant minus 3. So, and then divide by 2 times the a, that's 1. So, If we go through that, we can compute that out as a minus 1 in the case of using the minus. If we use the plus, it comes out to 3. So 2 roots. So if we factor the polynomial, it came out from x plus 1 and the other factor x minus 3. So the opposite sign of the 1 and the minus 1 and the 3. So there may be different ways you've learned and to factor polynomials, factor quadratics, but there's one way we can always factor. If we do the quadratic formula, we can factor any quadratic. Let's look at 4x squared minus 5x minus 6. Previously I wrote down the factors, but if we find the roots, we could check this out. So we get b is minus 5, so 5 plus or minus, we get the minus 5 squared, minus 4, a is a 4, and c is a minus 6. Divide all this by 2 times the a, which is 4. And so after we simplify that expression with a plus and with a minus, we get the case of 2 for a root and minus 3/4 as the other. So 4x squared minus 5x minus 6 would be, well, it has factors x minus 2, x plus 3/4. Actually, these aren't equal yet because the way I've written it, everything is monic, and the actual original polynomial, the leading coefficient is 4. So I have my monic factors, and then I also have that common factor of 4. Now, in a, what we might think of as a more aesthetic setting, we might take the 4, multiply into this second factor, and then write it in a way we might like to look at better, x minus 2, and the other factor being 4x plus 3. So if we don't want fractions, we can write it all out in terms of whole number, coefficients, and constants. Now, we can factor every quadratic. We can use the quadratic formula. But sometimes maybe the quadratic formula is a little bit of an overkill. So we might do certain types of quadratics, such as something like 3x squared minus 7. So the first degree term is missing. We have a square and a constant. So we could use the quadratic formula, but in this case we would be looking for solutions of 3x squared minus 7. And without the x term, we can separate constants and variables, and then solve for the variable. But now instead of an x, it's an x squared, so one last step, and we get the square root of 7 over 3 here with a plus or a minus, two possible roots. So 3x squared minus 7 would have the factors x minus a square root of 7 over 3 and x plus square root of 7 over 3. These being monic, I need the leading coefficient of 3 out front. Another case where we might not resort to the quadratic formula is when what we have is monic. Something like x squared plus 5x plus 6. So the leading coefficient is a 1. And so the constant, 6, is a product of the roots. And the 5 as essentially the sum of the roots. Actually, it will turn out to be negative, that value. So we need a sum of roots to be minus 5, and we need a product which is 6. So possibilities would be something like we could take 6 and 1. Those are factors of the product that make 6. But then if we took 6 plus 1 and changed the sign, that would be minus 7. So that doesn't work. So here I took two pluses to get plus 6. I could take negatives, but they would have to both be negative to give me 6. Now, if I take minus 2 and minus 3, add them together, change the sign, oh, I get the 5. So I found a factorization. So the factors would be x plus 2 and x plus 3. So I just considered factors of 6. Do they add up to 5? So that would be quadratics. If we move on to higher degree polynomials. So what we looked at with monics, product of the roots would still be the constant term. So even though it was higher degree, we might be able to come up with possible roots to check. And now the sum of the roots, changing sign, is still one of the coefficients. So you can find the leading term, look at the term that's 1 degree less. The sum of the roots should be the opposite sign of that coefficient. So you can use that same idea with higher degree polynomials to find possible things to check as roots. If we look at general polynomials, maybe something like 2x cubed minus 3x squared minus 8x plus 3. And you can look at a factor of a constant term and divide that by a factor of the leading term. So in this case, a factor of 3 divided by a factor of 2. So those are possible roots. So factors of 3 and 2, well, we could get 3 over 2, but also we could use negatives. So put into, but we could factors, each of these numbers also has a factor 1, so we could get 1/2 minus 1/2. Or we could take 1 and 1, and also 3 and a 1. So for nice rational possibilities, 3/2 is negative 1/2, 1, or 3, and they're negative. So a short list of things we might check. So we could begin through as example, we could take x equal 1 as a root and check. So it was 2x cubed substituted with a 1 minus 3x squared minus 8 times x minus 3. So if we substitute 1, we get minus 12. So x equal 1 isn't a root. So you could keep checking all of those. So in this case, 1, 2, 3, 4, 5, 6, 7, 8. We could do 8 checks. So I could go, let's check 3. So 2 times 3 cubed minus 3 times 3 squared minus 8 times 3 minus 3 And this time we get a 0. So we found a root, and x minus 3 is a factor of that original third degree polynomial. Now, here I would have to keep going through and check all of these 8 possibilities that I wrote down to see if any others might be factors or roots. So, which is possible. But we could take a method to check these roots a little quicker. So one terminology for this is synthetic division. Actually comes from something in numerical analysis called Herner's method, but synthetic division is a nice little name. And so what do we do? Well, the possible root that we checked before was 3. And we had the polynomial 3x cubed minus 3x squared minus 8x minus 3. So take those numbers, 3 for the root, and the coefficients 2, minus 3, minus 8, minus 3. So I've taken these numbers, the coefficients, just dropped the variable from all of the notation, but kept them in order. Now I go through and start with the 2 and just merely move it down and write it. The next step is to take the 3, multiply by that 2 I brought down, and bring it up. So that would be a 6 in the next column. Now, actually what I did in this first column was add 2 to nothing and got a 2. But now I get minus 3 added to 6, so which is a 3. And then I take 3, multiply again, and that becomes the number in the next column. So 3 times 3 is 9. I add in the column, and this time I get a 1. Take 3 times 1, move it up, add 0. So this last entry is a 0. So that means 3 is a root. If I get a different number at the end, it's not a root. Okay. So a little faster than substituting 3 in to the polynomial form. But besides that, we gain a little extra. We started 2x cubed minus 3x squared minus 8x minus 3. we found that 3 is a root, so x minus 3 is a factor. But actually I can read off the other factor. The coefficients left here, 2, 3, and 1, are the coefficients of the other factor. So 2x squared plus 3x plus 1. So doing it this way, I get a quick way of checking, do I get 0 when I substitute it in, but also it gives me coefficients of the factored parts. At this point we could factor further, because now I have this quadratic 2x squared plus 3x plus 1, and then I could possibly factor that. Now, if we have a root that's a fraction or a factor, that's not monic, we could take the fraction root and perform what I did with synthetic division as in the last example. And then I had to perform all of that with adding, multiplying with fractions. We can modify synthetic division so we don't have to use the fractions. So let's take example of the same polynomial we were working with, 2x cubed minus 3x minus squared there, sorry, minus 8x minus 3. And check a possible root. So when I listed possible fraction roots or whole number roots, one of the possibilities that came up would have been minus 1 over 2. We're looking at the factor x plus a half. But if we multiply that common factor, we might think of the factor 2x plus 1 instead of x plus a half. So one way or the other. So if we look at the root, we'll have to deal with fractions in our computations. And if we look at the factor, we're in many cases look at 2x plus 1 instead of x plus a half. So either we're looking at a factor that's not monic, so what do? Or we have to deal with fractions if we look at the root. So what we're going to do is either look at the root minus 1/2. So let's write the minus 1, which is just the numerator from our possible root. Now, as I did before, I'll list the coefficients of the polynomial. So 2 minus 3 and minus 8, and then on to minus 3. But now I'll modify. So as I move through here, I'm going to do some multiplications of these numbers. So now the denominator comes into play. So I put 2's as multipliers here, but I progress the power of the 2. So I start with a 1 and then a 2 to the first, 2 squared, 2 cubed until I finish. And so now I have minus 1. Instead of the original coefficients, I have 2, minus 6, minus 32, minus 24. So now all the numbers are still whole numbers, possibly with minuses. And I do the same synthetic division process. So I take 2 with nothing underneath, adds to 2, multiply by the minus 1, add in the column, multiply by the minus 1, add in the column, multiply by the minus 1, and finish. So I get a 0 here, so I get the root. The number I checked, minus a half, is a root. Now, as far as factors, if I look at this last row, 2 minus 8 minus 24, well, the modification I did at the beginning, I have to undo that. So I multiplied by extra 2's. Now I divide. So I take these coefficients, 2 minus 8 minus 24, and divide out. 2, 2 squared, 2 cubed. Okay. So I have one less term now. So where before I multiplied, I had one extra coefficient that didn't have a multiplier, but now I'm down to the other 3. So I divide by powers of 2, starting with 2. So this would be 1 minus 2 and minus 3. So it brings me back to a factorization. I had 2x plus 1. Or if I want to write x plus a half. And the other factor would be x squared minus 2x minus 3. So the modified numbers after I divided by powers of 2. Okay. So again, then I could look at factoring the quadratic. So actually I could factor this into 3 once I'm to this point. Because here this is a monic quadratic, so I look at products which make up 3. So I don't have too many choices. 3 and 1. The sum or difference is going to have to be this 2. So that should work out. As factors of 3 would be 1 and 3, one of which has to be negative. So either plus 1 minus 3 or minus 1 plus 3. If I use this combination, then the sum of the two is the minus 2. Now, we were looking at polynomials, and a lot of factorization comes in the form, we have a polynomial, what are the factors? So, but what if we get some non-polynomial expressions? Sometimes we get something that might have not perfectly a polynomial, looks a little bit polynomial. 3x squared plus 2x to the minus 3 plus 4x. It's not polynomial because the 1 power is negative, so it's not a nice whole number. It has a negative power. So we look at the least degree, in this case, minus 3 of the 3. So we have 2 minus 3, 1. So the least of those is minus 3. Take that power, x to the minus 3, and factor it from all 3 terms. So, if I factor out an exponent of minus 3, that means I'm going to have to add back into 3. So I get 3x to the 5th, 2, and then the exponent would be 0, so a constant, and then factor minus 3 out, leaves 4 here. And you can check that. If you multiply back, you would have minus 3 plus 5 as an exponent, which is the original 2. The middle one is we just factored out x to the minus 3. In the last term, if we multiplied x to the minus 3, x to the 4th, we would have x to the 1st. But in this process, we get a common monomial, one term factor, and then the rest of it is, a polynomial. So in many cases, we can bring something back to polynomials. A lot of times if we have sums of powers. Doesn't always work, but if the powers match up right with fractional exponents, we can work in the same light. So if we have 3x, the power exponent 3 halves, minus 2x with an exponent of a half, if you take the least power again of the two here in this example would be 1/2 power. Factor it out. Leaves a polynomial again. 3x squared minus 2. So if these were all half powers, 3 halves, 1 half, maybe 5 halves, 7 halves, those kinds of things, this would work out. So again, a nice one term common factor, and everything else left is a polynomial. Some other things that you can play around with if you don't like the form. So here I have a polynomial with fraction for the coefficients. Well, we can end up working without fractions if we take the common denominator so we have denominators as we look through the list. 3 and 5, common, or the least common actually, is 15. So here I've just written 15 over 15, complicated way to say 1. But if I leave 1 over 15 outside and multiply through by the 15 in the numerator, I get 10x squared minus 90x plus 21. So if I want to play around and not use fractions, I can have whole number coefficients. The same is true with decimal numbers. So if I have decimals, 2.8 x squared minus 6.2x plus 2, I can take whatever the decimal place is at the most, in this case a tenth, factor that out, which just leaves 28x squared minus 62x plus 20. Again, no decimals to work with. So if we like whole numbers, we can work around that.